Okay. One-sided limits and limits at infinity. We're going to talk about that this week. I'm just going to briefly touch on limits of infinity. We'll go over that more next week, but I'll talk about the rules. Okay, one-sided limits mean as you are approaching, so here's 0, 1, 2, right? As you're approaching any number, right? This is the right side. This is the left side of that number. So when it is saying, hey, all we care about is we're going to look at on this side, this means on the positive side. So even if it's a negative number, the positive direction of a negative number is on this side. All right. So let me erase all that. That was silly. Okay. So on piecewise functions and one-sided limits, notice this is greater than goes in the right direction, less than goes in the left direction. Same with greater than or equal. So if we want to look at a number from the right, we're going to be looking at this function because this says, oh, you're going to look to the right, the greater side of 0. All right, so that's the cool thing. If you can kind of remember that when you have one-sided limits, you can look at the inequality symbol and that will give you the direction. This is to the right of 0. So this is the work that you would show. You'd show the limit as x approaches 0 from the right. And notice this is a piecewise function. The only piece of the function that we're going to use is to the right of 0. And now when you substitute on ones that are this simple, you don't have to rewrite it. Negative 2 times 0 is 0. 0 plus 6 is 6. And you're done. Okay, this one's a little bit more complex. This is still negative 3, the right side. So this one's the right side. So the limit as x approaches negative 3 from the right. Now what I recommend you doing on this one is extracting that negative 1, then putting x plus 3. If you're not going to do that, if you don't like, I don't want to do that, that'll mess me up, then go ahead and put negative, put the x there. Because now, if you know that negative 3 is in there, opposite of negative 3 is 3. It just can get messy. The reason why I want you to, when these both have negative signs, to factor out a negative 1. Oops, factor out a negative 1. Well, now when you put a negative 3 in there, oh, negative 3 plus 3 is 0. Negative 1 times 0 is still going to be 0. You have to be really, really careful. And all my calculus kids, students, when they don't factor out negative signs like this, it's just really easy to mess that up. And I know you're going to have a calculator, but it's best practice to, just be very careful. Okay. Remember last week we talked about absolute value graphs. Rational absolute value graphs look like this. Okay, this is the parent graph, absolute value of x over x, or x over the absolute value of x. F of x is equal, right? Okay, if there's a negative sign in front, when you get done simplifying, then the graph, because essentially you know how things get reflected? This reflects up, this reflects down. So the numerator, or what used to be the numerator, will now be in the denominator, and what was the denominator will be, so it flips, it reflects the graph. Okay, this is the work that you're going to show me. Also, the lead number tells you how far away from 0. So we're going to go up 3, down 3. And the inside tells you, remember, whether you're going to shift left or right. So, and where the vertical asymptote will be. So on this one right here, I'm just going to put an equal sign. This has a negative x. I'm going to factor out a negative 1. That gives me positive x. But 1 divided negative 1 gives me negative 1. I'm going to do the same thing down here. I'm going to factor out a negative 1. And then that gives me x subtract 1. Okay. But now I can take the absolute value of this negative 1. The absolute value of negative 1 is 1. 3 times 1 is 3. So now we have the limit as x approaches 1 from the right. We have 3 times the absolute value of x subtract 1 over, 3 divided negative 1, so there's going to be a negative sign out here. Instead of leaving the negative sign in the denominator, we'll put it in the very front. Let me move this. All right. Now, this is one-sided. Because remember, a normal, if it's not one-sided and the graph is doing this, those limits don't match up. Those heights are not the same, so you'd say does not exist. But if it's one-sided, well, we know the height of one of the sides. So there is going to be, so what I'm going to want to see on these is I'm going to want to see the graph. So we're going to do this, look inside the parentheses, your absolute value. The opposite of negative 1 is positive 1. So at 1, that's where you're going to imagine that invisible asymptote is going to be. You don't have to draw it. And then we're going to go up 3 and down 3. Over to that 1. And this is a negative graph. So up here, the graph is going to go to the left. And in the denominator, the graph is going to go to the right. And what we're looking at is as we approach 1 from the right, our height is down here at negative 3. And this is the work that you would show on these. Let's do one that's not negative. All right. So for this one, notice the numerator and denominator do not match up, but in the numerator, a 4 can be factored out. And this is positive, so we don't have to worry about the graph being flipped. And so the opposite of positive 3 is negative 3. And then we're going to go up and down 4. And then I'm going to want to see it labeled at 4 and negative 4. And since this is positive, the graph is doing this. This is negative. And we're approaching negative 3 from the left. And the left is over here, and we're at a height of negative 4. So the limit as x approaches negative 3 from the left ta-da, I do want to see the graphs when you're doing this. So on an exam, I would expect to see the graph of this, and then I would expect this work to be shown. All right. Now, we're switching back to not one-sided. So you look here, is there a left or, whoops. Is there an elevated positive or negative sign? If there's not, then you're just looking at both pieces. But here's the tip. Notice these are not inequality signs. So let me show you what the graph is doing on these. So this says at -2. Well, at -2, not as it is approaching, but at -2. So this one, instead of getting a solid line, because now remember, we're talking about limits. We're talking about height. At -2, we're at a height of -1. So you put a solid dot. This graph right here is a upside down parabola, and it's saying it's everywhere but -2. So notice this is -x squared minus 2x. That means plus 0, right? So we know that I'm going to factor out a -x, and then that will be x plus 2. So we know that where x is equal to -2, and where x, so there'd be a solid dot there. That'll be a root. But this says x can't touch 2. So we're going to put a hollow dot there. And then that graph is doing this. But what we care about, and again, you can type that into Desmos. You don't have to draw this out. Even on a test, what I'm wanting you to focus, when it says as x approaches a number, and it's neither left or right, it's asking about this one, because this is just a solid dot at -2. What we're asking is, as you're approaching -2, well, as you're approaching, so for example, I'm going to zero out, we're going to cover this completely. So now look at what's happening. This graph is doing this. Look at that. So as we're approaching -2, that height is approaching 0. So the limit as x approaches -2, we know we're going to use this function. And that height is approaching 0. Okay, so what I recommend you do here, I recommend that you go ahead and do one of two things. You could factor out a -x, or just factor out a negative sign, and then put x squared plus 2x. Just so that when you're plugging into x's, -2 squared is 4. 2 times -2 is -4. That's 0. The opposite of 0 is 0. It's just good to be in the habit of factoring out those negative signs. So this is only work that you would have to show me on this one, but I recommend using Desmos to confirm that that's what it's talking about. All right. Yeah. So on this one over here, again, we're going to look as it's approaching, and we're going to substitute 0 into, so right away we know that height is going to be -2. This height is -3, but this is the approaching height. In this case, it would be probably doing this. And that's the exact height. So the work, the limit as x approaches 0, x squared minus 2x. And we know that when we substitute zeros in, zeros out, and what you have left is the height of -2. Okay. Now we're going to move down here. Okay, these are not one-side limits. I think I went over these. I'll go over it really quick. Quadratics, you're going to factor. Factors of 3, that add up to -4. Well, that would be -3, -1. Right? And then notice, those cancel. That also means there will be a hole in the graph. But then you're going to show me this. And now when you plug 3 in there, 3 subtract 1, we're at a height of 2. This is the work that you'd show me on that. All right. I don't think we did one of these. We're going to do some simplification first. In the numerator, since the rational, the complex part is not there, I'm just going to rewrite x as x over 1. It'll simplify things later. Now, all of our attention is down here. So we have 1 over x plus 1, and now we're subtracting something. We're subtracting 1. But instead of 1, we want them to have the same denominator. Well, you'd multiply top and bottom by 1 plus x. So this would get a 1 plus x. And that makes sense. 1 plus x divide 1 plus x, assuming that x is not -1, those cancel out to 1. So we're in good shape there. So now we have the limit. Well, before I even finish, we're going to keep simplifying. So we have, I'll do it over here, x in the numerator. And now look at what we have. 1 subtract 1 is 0. And then there's still a negative sign, and that will distribute. So now down here, we have -x over, because these denominators are the same. So when things are combined, so we don't want a fraction over a fraction, so we're going to multiply by the reciprocal. And then those cancel, but then we have to do the same thing here. Well, diagonally, that's going to cancel. Those x's cancel, leaving -1. And so now what you have is the limit as x approaches -1. And we have a -1 down here. We can just put that negative sign in the front of the fraction. And now we're going to plug in -1. -1 plus 1 is 0. The opposite of 0 is 0. If you need help with those, okay, I don't think that we did these. These are rational, meaning fractional with radical signs. Remember when you did these in probably Algebra 2 pre-calc, when you're just rationalizing, say you had 3 over root 5 plus 4. To rationalize the denominator, you multiply numerator and denominator by the conjugate. And then root 5 times root 5 is 5. positive 4 times negative 4 is negative 16. And in the numerator, you'd go ahead and multiply that out. Okay, so the same thing applies. Part of the reason you practice some of those skills, so when you get to calculus, you know how you already have those skills. All right. So you look at where the radical sign is. It's in the denominator. So the conjugate would be that radical sign plus 2. Okay, here's a tip. On the part where you're not multiplying by conjugates, down below, those are the conjugates. In the numerator, don't do the distributive. Leave it exactly as it is, even on the next step. So the limit as x approaches 2, in the numerator we have x subtract 2 times the square root of x plus 2. And technically it's best practice to close the parentheses under the radical sign, even though CUDA software doesn't. Now, in the denominator, you multiply the first times the first, or radical times radical, the radical sign goes away. So that's x plus 2. And then what we have is negative 2 times positive 2. Well, that's negative 4. So in the denominator, 2 subtract 4 is negative 2. That's pretty crooked. Well, look at what we have. We have this x minus 2. Those cancel. So now what you're left with does not need to be that big. All of this stuff in the numerator. And then when you substitute, 2 plus 2 is 4. The square root of 4 is 2. 2 plus 2, we're at a height of 4. Now, if you're very clever, I want you to notice something. Remember when we first identified the conjugate and it's in the denominator? That conjugate is now in the numerator. So when you're doing these, if you'll notice, we're going to multiply by the conjugate. What do you bet that the simplified answer is now going to be the reciprocal of the conjugate? So let's try it out. So in the numerator, root x times root x is x. Negative 1 times positive 1 is negative 1. And in the denominator, we have x minus 1, root x plus 1. Oh, look at those cancel, leaving 1 over the conjugate term. So I was correct. So that's just, if you start to notice patterns, that saves you a lot of time. Now, while you're doing the test for me, do I want you showing the work? I do. But what that means is, as soon as you identify the conjugate and you know that the answer is going to simplify to the reciprocal of whatever the conjugate is, that will be a way for you to check your own work. All right, now we're going to substitute 1 down here. Whoops. Except for I meant to highlight that. The square root of 1 is 1. So 1 plus 1, the denominator, is 2. All right. We'll talk about the trig ones later. Okay, these one-sided rational. So look at a number line. to the right is over here. So let's say that's negative 2.9999999, infinitely close, right? Well, negative 2.9999999 plus 3, you're going to have this really small, since negative 2 is, negative 2.99 is smaller than positive 3. This is going to be a positive. Let's go out several zeros. All right? Well, if you type that into your calculator, negative 2 divided by that, 1, 2, 3, 4, 5, 6, 7, I think, I could be off by 1. You're going to have 20 million. Well, if we're closer to 0, well, now it's 200 million. Even closer, that's 2 billion. The point being, the closer you get to 0, the closer you're going to get to either positive or negative infinity. In this case, since this is negative 2 divided by a positive number, you're headed towards negative infinity. So the graph looks something like this. Notice that the vertical asymptote will be at negative 3. And on asymptotes, there's a couple things happening. So from the right side, the graph is probably doing that. On the left side, so notice on this one-sided graph, the closer you get to negative 3 from the right side, so negative 2.99999, keep going, the farther into negative infinity that it gets. All right. Now, on the ones here, you can, trying to think if on these do I want you to do the factoring. Yeah, you could do that, because I think on the ones where they might cancel, so factors of positive 6 that add up to negative 5. Let's see if that helps. Sometimes these don't help. In this case, I think it does help. Okay, so we're approaching 3 from the right, so that's going to be 3.0000. So now you've got 1 over this infinitely small number, right? So that's going to turn 1 into a trillion. So we know that's going to be positive infinity. All right. Now, we'll talk about the limits as they head towards infinity, probably more on Friday and then the following week. So what we're going to be looking at now is as the graph is headed towards, positive infinity or negative infinity. So let's look at, this is x to the 4th. So let's say the graph looks like this. Well, look at what's happening. As you go this way, the graph is going up. If you go this way, so in this case, as we're headed towards negative infinity, the height is getting infinitely taller. So positive infinity. Now, if that would have been an x cubed, and that graph looks like this, now as we head towards negative infinity, that graph is headed downward, so that would have been a negative infinity. So you do have to pay attention. So again, using Desmos is a good idea, or you should know the parent graphs by now. If it's an even polynomial and positive, right? So, smooth curve. So an x to the 6th, an x to the 2nd, right? On even functions, the ends are going in the same direction. odd functions, so y equals mx plus b. Opposite directions, y is equal to x cubed. So odd exponents, the graphs go in opposite directions. All right. Now, some would ask, can you just type in a large number and do it that way? Yeah, so could we put, let's even just do negative 10. Negative 10 to the fourth is 10,000. Well, these numbers, doesn't matter what they are, doesn't even matter if they're negative. They're not going to get anywhere close to positive 10,000, so you know that that's positive infinity. So that could be an approach on a test if you were freaking out about it, unless I told you to graph it. So this is a negative x squared. So as you're headed towards negative infinity, right away, but the other way to do it, notice that says negative. Well, if you put negative, let's say put negative 100 squared, well, negative 100 squared is positive, but the opposite of positive is negative. So if you just put negative parentheses negative 100 squared, enter, you're going to get a large negative number, and that's how you'll know negative infinity. Okay, so here are the rules. And then I'm going to stop because this is a long video. The rules of limits at positive or negative infinity. So if they're a polynomial, the answer is going to either be positive or negative infinity, because we know what the graphs are going to be looking like. You're either headed upward or you're headed downward infinitely. All right, all polynomials. Okay, the next situation is when you've got x to the lower, a lower exponent value than the exponent, right? So maybe you would have an x squared, blah, 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 over x cubed, blah, blah, blah. The height of that limit will be 0. This is why. Because on any rational functions, when the exponent in the numerator is lower than the exponent, there is a horizontal asymptote at 0. So maybe the graph is doing this. And then look at, as we head towards negative infinity, that height can only approach 0. If we're headed towards positive infinity, that height can only approach 0 and not pass it. But the rule is, if the degree in the numerator is lower than the degree in the denominator, you're going to be approaching 0. Rule 3. If the degree in the numerator is the same as the degree in the denominator, so let's say you have 3x cubed over 4x cubed, well, the rule says there's going to be a horizontal asymptote at the ratio. The height will be the ratio of a to b. So in this case, 3/4. So this example, so if this is a height of 1 at 3/4, that's where the asymptote's going to be. So it's probably looking something like that. Okay, that's rule 3. When the degrees in the numerator and the denominator are the same, you're going to look at the lead coefficients, and that is going to be the height, because that's where the horizontal asymptote will be. Fourth is when the degree is higher than the degree in the denominator. If the degree in the numerator is higher than the degree in the, so like x fourth over x cubed, blah, 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 then what you end up with is a slant asymptote, and your answers are either going to be positive or negative infinity. So for example, you might have A vertical asymptote. Oh, by the way, for these right here, there's almost always never going to be, I don't want to say never completely, because I don't remember if that's an absolute rule, but generally in this class there will not be a horizontal asymptote. But there will be a slant asymptote. We'll talk about how to find that slant asymptote later. So let's say the slant asymptote looks like this. And the graph, and there'll be, so what you're going to be doing is you're going to be looking at negative infinity, positive infinity. If you're headed towards positive infinity, oh, look at that graph is going up. If you're looking at negative infinity, oh, look, that graph is going down. All right, those are the rules of limits at infinity. We'll practice those. Notice on this one, cube root, they're both the cube root. That follows rule 3. So the cube root of 1 over the cube root of 1 is just 1 divided by 1. So that's the height of 1. Oops. Yeah. The cube root, negative 1. So, no, that's still going to be a height of 1 because it's the ratio of the numerator over the denominator when the exponents are the same. All right. Have a good week.